Hello, AP Electricity and Magnetism student. Welcome back to our new video. In this video, we are going to solve 2022 past paper, question number 1, set 1. A non-conducting sphere of uniform volume, charge density is surrounded by a thin concentric conducting spherical shell, as shown in the cutout view. The sphere has a charge of minus q, so the electric charge here is minus q, and the shell has a charge of plus 3q. So the shell has a charge plus a 3q. Now notice here we didn't specify whether the 3q is located in the inner surface or the outer surface. The netted charge on this shell is a plus a 3q. The radii of inner sphere and spherical shell are r and 4r respectively. So for the smaller one, it's r, and for the largest one, it's 4r. Now we need to determine the charge of outer surface of the shell. Now what will be the charge here in the outer surface? Now to determine that, we know that the netted charge of any object is given by, if it's conductor, it will be given by the Q inner plus the Q outer. So for a shell, the electric charge net, it will consist of the inner distribution of charges and for the outer distribution of the charges. The total will give me the Q net. Now, here we are interested in finding the Q outer. So let's change the equation a little bit by moving the Q inner to the other hand side. We can write a formula for the Q outer. So Q outer is given by Q net minus Q inner. So Q outer is equal to plus the 3Q, this is the net, minus Q inner, and the Q inner, in the inner surface, we have electric charge equal to the electric charge in the sphere but an opposite sign. Since the sphere carries a charge of minus Q, the netted charge on this face will be equal to the charge located in the center. So since here we have minus Q, the electric charge here, the distributed one on this surface, on this face, will be plus Q. So the inner will carry this charge plus Q. And finally, plus the 3Q minus Q is equal to 2Q. So the charge carried by the outer face is plus 2Q. Let's go next. Using Gauss's law, derive an expression for the electric field at a distance r from the center of the sphere for r less than capital R. Let me remind you that the capital R represent the charge or the radius of the small sphere. We need to set our Gaussian surface to be exactly less than this capital R. So somewhere here. This is my Gaussian surface. Now express your answers in terms of Q, R, small r, and the physical constant as appropriate. Now back again, we need to use Gauss's law. We know that applying Gauss's law allows us to determine the relationship between the flux and the Q enclosed. Now let's start by evaluating the left-hand side. We know that the integral of the E dot dA is equal to E 4 pi r squared. Since our Gaussian surface is spherical sphere or spherical surface, then the area of the surface will be written as 4 pi r squared. The left-hand side, no need to evaluate it. You just need to uh, look at the symmetry that you have choose, and the final result will be fixed or will be written uh, directly without any derivation. Now, this is the left-hand side. What about the right-hand side? For the right-hand side, we have the Q enclosed over epsilon zero. So we need to re-express Q enclosed according to the sphere that we choose. Now, the sphere is the insulator sphere. This is insulator. We know that the rho for insulator is given by the total Q over V, uh, which means the total Q is given by minus Q. According to the given, we know that the charge in this sphere is minus Q. Now the volume of this sphere, the total volume will be 4 over 3 pi r cubed, where r is the radius of this sphere. Now we have expressed the density of the charge by using information from the sphere itself. And now let's use this density to evaluate the Q enclosed. Now Q enclosed is written according to this formula, rho is equal Q over V. So if we need to find the Q enclosed, we must multiply rho times V enclosed. The density is given by minus Q over 4 over 3 pi r cubed multiplied by the V enclosed. The V enclosed is the volume of the Gaussian surface of a radius r. And it's written as 4 over 3 pi r small cubed, where r small here represent the radius of the Gaussian surface. Now, um, okay, so we can cancel 4 over 3 with 4 over 3, pi with pi, and we will end up with this relationship, sorry, minus q r cubed r cubed. So this is the relation that represents the electric charge in the closed surface. Now let's collect this information together. In the Gauss's law, we know that the right-hand side of the equation represents Q enclosed over epsilon zero. Now we know that the Q enclosed is given by minus Q r cubed over epsilon zero, which means the Q enclosed over epsilon zero can be replaced by minus Q r cubed epsilon zero r cubed. Now we have on the right hand side this, we have on the left hand side this, so right hand side equals left hand side, and we would get that E is E 4 pi r squared equals minus Q r cubed over epsilon zero r cubed. Now let's move 4 pi r squared to the other hand side. We just divide both sides with the 4 pi r squared, and we will get that the E is equal minus Q r cubed 4 pi r squared epsilon zero r cubed. Now we can cancel r squared with r cubed, but we will still have survived r in the numerator. And finally, the electric field will be written as minus qr 4 pi epsilon zero r cubed. Now, the magnitude of the electric field at r is equal capital R, it's equal to 8 Newton. So when our Gaussian surface exactly has a radius exactly equals to the radius of the sphere, the electric field becomes 80 Newton per coulomb. Now the question is, what will be the value of the electric field at a distance 2r? So if we increase our Gaussian surface, what will be the electric field at this point, which is equal to 2r? Now, first of all, for insulator, the electric field will be written in this way. Q 4 pi r squared epsilon 0. Let me write epsilon 0 first. So this form can be used only if we set our Gaussian surface inside the sphere. And once we cross the boundary, we will treat the electric charge, the sphere, as if it's a pointed charge. And we know that for pointed charge, the electric field will be written in this way. Now let's focus on the relation between the electric field and the radius or the distance, radial distance. Now this relationship is inversely proportional with r squared. So E is inversely proportional with r squared. Or you can say directly proportional with 1 over r squared. Because the Q will remain the same, the pi, E0, and 4 are constant, so it's enough to analyze the relationship between E and the r squared. Now, since we have doubled the distance, let's apply factor of change. Then what will happen to the electric field if we double the distance? So this Q remain the same, the 4 remain the same, the pi, the epsilon 0, only R has been changed into doubled. So 1 over 4, which means the new electric field is 1 over 4 of the old electric field. Now, the old electric field is 8, and 1 over 4 times 8 is equal to 2 Newton per coulomb. Derive an expression for the absolute value of the potential difference, which means we need to find the delta V between the outer surface and the sphere and the inner surface of the shell. Express your answer in terms of Q, R, and physical constants as appropriate. Now we know that the potential difference is given by this formula, which is minus E dr. And why did I use this formula? Because this formula is a relationship between the potential difference and the electric field. We have already derived the relationship for electric field inside the sphere and outside the sphere. And we found it to be inside the sphere like this. And outside the sphere is just the normal formula that we have used to use for a pointed charge. Now, since we are looking for the delta V between the outer surface, so we cross the surface of the sphere and the inner surface of the shell, then we don't use for electric field this relationship because this is valid inside the insulator sphere. We're gonna use the other relationship, but because this is can work for any region between the shell and the sphere. So let's substitute delta V is equal minus. Now, let me bring your attention that this is just the general form. And the reason why did I write it in this way? Because I just need to evaluate the relationship between E and R. However, don't forget that the electric charge in this problem, the electric charge of the sphere carried by the sphere is negative. So make sure to write the negative in the relationship here. So it's negative the charge over 4 pi epsilon 0 r squared dr. Now the boundaries are from the surface, which means I'm gonna set my boundaries to start from R up to the inner shell, and the inner shell, the radius there is 4r. So delta V is equal, minus times minus is plus. So from R to R equals 4R. You can write it in this way anyway. So we can write it like this. So from R to 4R. Now Q and 4 pi epsilon 0 have nothing to do with the integration. So let's place them away. Remember that minus with minus cancelled out over 4 pi epsilon 0. 1 over R squared dr. Now we know that the integration of 1 over R squared dr, it will be equal to minus 1 over R. From R to 4R, which is equal to Q over 4 pi epsilon 0. So minus 1 over 4R minus 1 over R. Now we have two minuses here, minus because of the formula here, and the second minus because we need to find the difference between the boundaries. Now finally, the delta V is equal. So minus times minus is a plus. So plus 1 over R, I prefer to write it first. Minus 1 over 4R. Now we can work on the common denominator in order to find more, let's say, a more clearer final relationship. So I will multiply here by 4 and here by 1. So delta V is equal Q over 4 pi epsilon 0. 4 over 4R, same denominator, and here minus 1. 4 minus 1, technically it's 3. So the final answer is a 3Q. So here we will have a 3 times Q, 3Q, and 4R times 4 pi epsilon 0. 4 times 4 is 16 pi epsilon 0 R. And this is the relationship of the potential difference from R, from the surface of the sphere up to the 4R. Now, in the following regions or following axes that include region I, double I, and triple I, sketch a graph of the electric field as a function of distance R from the center of the sphere. Okay, first of all, the electric charge of the sphere is minus Q. Now, let me explain this. Now, here in this graph, we need to plot the electric field with respect to the distance, and we have a certain distances that we need to pay attention to. Now, for the first distance is from 0 to R. This includes only the insulator sphere, and the insulator sphere carries a charge of minus Q. So you should expect to have a linear electric field because the relationship of this electric field is given by E is equal minus QR. This is what actually we have derived over 4 pi epsilon 0 R cubed. So the relationship will be linear. But since we have negative, we need to reflect this linearity downward. Now, then what would happen to the electric field once we cross the boundary? It will start to decrease. Let me remind you with the graph for the insulator. It will be look like this. Now here also we will follow the same strategy. It will decrease without touching the 0 until we reach the 4R. Now after that, the sphere suddenly, let me go back to the sketch. The shell, remember that the shell has two faces. One of the faces is positive, the other one, the second face is plus a 3q. So once we cross the boundary of the sphere after 4r, the sphere becomes positively charged with a plus a 3q, with the shell at least. This shell, I'm talking about the shell, the solid shell. And once we cross the boundary, we are getting away from the sphere, the electric field will decrease. But how it would decrease? It will decrease um, exponentially. So suddenly the electric field will come out from nowhere here and decrease to zero. Now, on the following axis that include regions I, double I, triple I, sketch a graph of electric potential as a function of the distance from the center of the sphere. So again, we're going to start from the center of the sphere up to the third region. Now, the first region represents the insulator sphere. The second region is the distance between the insulator and the first or the inner surface. And then third region, when we cross the third surface or the fourth surface, the outer surface of the shell. So here we need to know what will be the potential or how would the potential varies with respect to R. Now to do so, let me remind you that in the first region, the electric potential at any point will be given by Q over 4 pi epsilon 0 R. Now this electric potential will start to be negative because the charge there carried by the sphere is negative, and it will decrease as we keep moving away from the charge. Now, as we keep moving away from the charge, let me go back to the sketch. We are getting closer to the positive shell, right? So we know that as we move from the negative sign to the positive signs, we are moving from low potential to high potential. So the graph now will increase slowly as we keep moving away from the charge. Now, again, here we have the sphere, the insulator sphere, and then the shell. Now, when we cross the boundary of the shell at 4R, we are getting away from the positive charge, which means the electric potential will decrease now as we're getting away from the charge, because we are moving from high potential to low potential. So, in a briefing, low potential at negative, as we keep moving away from the low potential toward the positive phase, it means we are moving from low potential to high potential. And then when we cross the boundary of the sphere or the shell, and we start moving away from the shell, it means we are moving away from the positive, and that means the potential is decreasing since we are moving from from high potential to low potential. That's it for today. Thank you for watching, and see you in a new video soon.